Welcome back, folks, to another lesson. Today we're going to be looking at linear modeling, which is really just a way of saying we're going to be looking at scatter plots. So let's start by trying to figure out why this might be important. Well, let's say you decide that you're going to sell snow shovels during the winter. What might you want to look into to determine how much you're going to sell? Well, it might be important to look at the temperature. It might be important to look at the weather or the precipitation over that entire time. And so what we would do is we would compare the temperature or the weather to how much snow we get or how many shovels we can sell, and we can more accurately determine how many shovels we should be buying. And this leads us to a scatter plot. All a scatter plot is it's a way of comparing two quantitative variables. And so what this means is we can look at two different things and see whether or not they have some sort of correlation. What's a correlation? Well, correlation is a measure of the strength and direction of the relationship between the two variables. We have actually three types of correlation. The first type of correlation is a positive correlation, meaning that as whatever your independent variable is increases, we also expect our dependent variable, or the one on the y-axis, to increase. So this might look something like now it's not saying that, every time we increase, we're definitely going to get an increase in our dependent variable. But what it's saying is we have a trend where as we increase our independent variable, our x variable, we increase our y variable. The flip side of this is a negative correlation, which means that as we increase x, y is going to go down. So we might end up with something looking more like this. Again, doesn't have to say that every time we decrease, we go down, but the general trend, and that's all correlation is a trend, is that we are going down. Then finally, there's no correlation, which is as we increase our x variable, we have no clue what's happening. It's just all over the place. So these are three types of correlations. Let's try to figure out a couple of practice problems, what the correlations for these would be. Starting with, if the temperature outside and the number of ice cream cones sold. So if the temperature outside is increasing, what do we expect to happen to the number of ice cream cones? Well, it would also be increasing, making this a positive, negative, or no correlation. Well, as one increases, the other increases, so this is a positive correlation. What about the outside temperature and your heating bill? As the outside temperature increases, what would we expect the heating bill to do? And would that give us a positive, negative, or no correlation? Well, as our outside temperature increases, we're going to have to heat less, so our heating bill should probably go down. One going up and the other going down, that is a negative correlation. What about the number of letters in your name and your height? As the number of letters in your name increases, what happens to your height? Does it increase, decrease, or is there no correlation? We expect no correlation. And you could have a super short name, it could be Tim and be 7 foot tall, or you could have a super long name and still be 5 feet tall. There's no correlation here. And elevation and temperature. As elevation increases, do we expect temperature to increase, decrease, or have no effect? We expect temperature to decrease, meaning that this would give us a negative correlation. How do we measure our correlation? Well, we have a really nice tool for measuring and determining what our correlation will be like. We call this our correlation coefficient. Your correlation coefficient is just the letter R, and your correlation coefficient goes between -1 all the way up to +1. All the way up to +1. The closer you get to 1, either -1 or +1, so we'll just call that bigger. The bigger you get either direction, the stronger the correlation, and if you're close to 0, there's a lot to put down here. If you're close to 0, there's a weak correlation or no correlation, meaning that your trend is not super strong. And then also, we look at the sign. So the sign of R tells us the correlation. Tells us whether it's positive or negative. So by -1, we have strong and negative. At 0, we're looking at no correlation. And at 1, we're looking at a strong positive. So let's get some examples of this. If we had something like our correlation coefficient was -0.9, what would that mean? Well, it's close to -1, meaning it's strong, and it's a negative correlation. Strong meaning our trend is close to a line. What about something like R is -0.4? Well, now we're dealing with a negative still, but we're weaker. Actually, let's make this 0.3. Now we're dealing with something that's weaker, meaning we have some negative trend, but it's not super close to a line. So we might see something where it looks generally like it's going down, but it's hard to say. At R is equal to 0, we have no correlation. We just expect it doesn't really matter what the relationship is between the two variables. Then as we continue onward, if we get something like R is 0.2, it's still weak, but this time our sign is positive, so our correlation is vaguely positive. Right? It's not really a line. We just almost can think that it might be going up. And then if we get close to 1 again, let's say R is 0.8, then what we can say is, okay, this is going to be close to 1, so it's strong, and it's positive. So we expect to see pretty close to a line there. So we have some practice. It's always hard to determine what exactly you should be going with, but what would we expect the range for this to be? What might the R value be for this? So this is pretty strong and it's positive. a good guess might be something like something between R is 0.7, maybe 0.8. What about this one? This one, it's hard to say. There might be a small positive correlation. There might be no correlation. Can we see it sort of going up? Maybe. I might put this slightly positive, like R is 0.1. And what about this? Well, it's negative and it's pretty tight. It's pretty close to a line here, meaning that this would be pretty close to -1, maybe negative 0.95. And the closer we get to this, we have less use for our line of best fit. But what a line of best fit is a way to get a trend line from this. Our definition of a line of best fit is the line that most accurately represents the data. Now in science classes, what you've done is you've taken a ruler and you've sort of guesstimated, you tried to shoot it. There's a fancy math formula that you can use for it as well. However, we're not going to use that. We're just going to let our calculators do that if we ever need our line of best fit. What is extrapolation? Well, extrapolation is using the line of best fit to try to fit data outside of where your data is. So what's extrapolation? Well, it's making a prediction but it's outside of your given data, right? It's extra, it's external, so it's outside of your data, given data. And we have to be careful with this one because we don't know that any trend will continue outside of our data. It may just be that it suddenly changes. So we can do this, but we have to be cautious about it. Okay, so if extra was outside, extrapolation was outside, interpolation, right, like interpol, not really a good example for this, is making a prediction inside of the given data. But most importantly, because we're dealing with scatter plots, we have to remember how to make scatter plots and how to find lines of best fit and such. So let's start by making a scatter plot, and then I'll show you how to do these inside of your graphing calculator. So we have age and height here. I expect age will probably be our independent variable, so it goes on our x-axis, and height will be on our y-axis. It's our dependent variable. Now let's make our values. Let's see, this goes all the way up to 63, so let's go up by tens. This is 10, 20, 30. And our age goes up to 18, so let's go up by twos. So that's going to be 20. This will be 2, 4, 6, 8, 10, 12, and so on. And let's create our scatter plot. So starting at the year, or at age 7, we see someone who is at 48 inches, so close to 50. At age 8, we have someone who's 51, so it's going to be a little bit higher. At 9, 52, so right about in the same area. At 11, we had 56, so a little bit taller. 15, we had 60, so we're all the way up here. 17, we had 61, so about the same. and 18 we had 63, so a little bit taller. And now we see that there is sort of a good positive trend in here. But let's figure out how we see the actual line of best fit in our calculators. So I have my calculator on. First thing we're going to need to do is make sure that we can actually get all the information we need. So what we're going to look for, we're going to hit second 0. So we're going to get to this catalog. Only ever have to do this once. And we're going to search until we find diagnostic on. Once we find that, we're going to hit enter and hit enter again so we see that diagnostic on is done. Now we're good to go on finding lines of best fit and correlation coefficients. So how do we do that? Well, to make any sort of scatter plot or any sort of data, we want to go into our stats menu because scatter plots are part of statistics. From here, we're going to edit our lists. And if you have information in the list, just feel free to go through and delete all of that. And now we're going to put into L1 all of the values in the first column and into L2 all of our values in the second. So we put in 7, 8, and all of your values into the other column. So 48, 51, 52, 56, 60, 61, and 63. Once you have all of that, you should be good to go. Your list should be the same length, so make sure they are. Then we can quit out of here. And now we're going to want to do some calculations. We're going to want to see some information on this. So we can do a linear regression. Linear because we're looking at a line, and regression just means we're doing some math to try to figure out what the line is. So to find our line of best fit, we go to Stat, Calc, Linear Regression. Now you may get something like this, you may not. Either way, you should just be good to go through, press enter, 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 and you'll get some information. It'll look like this. It'll say y is equal to ax plus b. And it'll say, well, a is this, b is this. We have r squared, which we're not going to worry about. But hey, there's r. So let's put down all of this information. Our line of best fit will be our height, which is h, will be equal to 1.251 times our age plus 40.671. Let's see if I can remember that. So when we're making our line of best fit, all we do is we say y, or whatever our variable is equal to a, which is 1.251, x, or a in this case, plus b. We put down our correlation coefficient, which is 0.985. What does that tell us? It tells us that this is super strong and super close to a line. This is why it's really handy to have your calculators for this. It just does all of the math for you. Now let's do another problem. For this one, we do need to make a scatter plot, so we'll start there. We'll make the equation. Then we have a couple of more questions. But let's get started with the scatter plot. Go ahead and make your own. I'll come back and fill this out when I am done. And so what you end up with is some sort of scatter plot that looks like this. Now, let's put this into our calculator so we can find the equation and correlation coefficient. We have our calculator up. What do? We go into our stat menu. We try to edit our list. And now we're just going to put in all of these values. So let's put these all in. No, it's going to take too long. I'll just come back when I have all these in. Make sure you've put all of your values in. All right, now that we have all of our data in, and we make sure our lists are the same length, we're going to do a linear regression. We're going to find our line of best fit, which we do by going into our stat menu, into calculate, and finding our way down to lin, or linear regression. Again, we can just click right through this and calculate. Once you do this, we'll find that we get y is equal to ax plus b. We have a, we have b, and we have r. So we're going to copy this information down onto our equation and correlation coefficient. And what we're left with is our equation, which tells us that we go up by about $0.50 for every dollar we earn when we're talking about cars in comparison to salary. Now this next question asks us, what's the likely car price for a salary with 60K? Well, how are we going to figure that out? Car price was our y value, it was our dependent variable, and salary was our x value, or our independent variable, meaning that all we need to do is we can just put this value in for x, sub this in for x, throw it into our calculator, and find out what we get. So let's go ahead and do that. I have a calculator right here. 0.522 times 60 plus 899.98. Now, if you think you got a really low number for that, it's because we're dealing in thousands here, meaning that this is not 60, this is actually 60,000. So let's put that in instead for x. So 522 times 60,000 plus 899.98 tells us that the average car, or we expect somebody with a salary of 60K to have a car worth $32,219.98. So this is what we estimate our car will be worth for someone with a salary of 60K. Again, what do? All we do is we take our independent variable, we sub that value in for x. Now here's the question, was that interpolation? Was it inside of our data or was it outside of our data, extrapolation? Well, we look, 60,000 is very much inside of the data that we have, making this interpolation. Meaning we're also good to go, we don't have to worry about being careful about extrapolating. Right, that's our lesson. Your homework will have to deal with finding the equations, finding correlation coefficients, and determining correlations. Remember all of the calculator stuff you just learned, and I will see you for our next lesson.